So welcome back to chemistry class. So previously we have discussed about electromagnetic spectrum, that is how the light can be classified into different kinds of frequencies and the wavelengths and their names like cosmic rays, X-rays, UV rays, infrared rays, microwaves, and between UV and infrared you have the visible region, right? So that part is done. Then now as electromagnetic spectrum we have observed, we can see that whatever the light is there, that is in terms of energy. Light is a form of energy and this is also quantized. So light is emitted in packets of energy, what we call them as, right? And the concept based on that is E is equal to h nu, right? Where h being the Planck's constant, which is 6.626 into 10 power minus 34 joule second, and nu is the frequency of the radiation emitted. So thus light usually emits like any substance, like maybe it can be extended even to the radiations, thermal radiations also, like h nu, 2h nu, 3h nu, nh nu. So in packets of h nu. So h nu is the quantized form of the energy. Okay, and then electromagnetic energy can be gained or lost in discrete values and not in continuous manner. Definitely it is not in continuous manner. This is what Planck has proposed, and thus it is called Planck's quantum theory. So it is quantized, energy is quantized, as well as it is like in discrete values. That means it's not continuous, like each baggage, how like in case of when your luggage is moving on a belt, in either you can see that in air, what do we say, airports, as well as some goods being like packed and then moved on conveyor belts in factories. You can see how they continuously will be moving on the belt, but each packet is different. Each packet is different. Likewise, this is also in discrete. Light is emitted or absorbed in discrete manner but not in continuous manner, and that emission is in packets. And those are all group of collection of group of wavelengths. So this is what Planck has proposed for the light. And then next, as we proceed, like how this happens, this particular wavelength, a particular wavelength will be emitted, and that particular wavelength will have a color if it is of visible radiation, is it not? So that means every substance has its own color, right? So that we are going to see now in an activity given in your textbook. So here cupric chloride is taken. Cupric chloride means it's a combination of copper and then chlorine, and this is mixed and made as a paste with the help of concentrated hydrochloric acid. Please try to remember the names, dear children. This can be asked as 1 mark question or half mark question, which is mixed with what and what kind of color is emitted. That is also very, very important question, and this at least one will be asked from this chapter based on the color composition and what is done and what is mixed. Right, so cupric chloride mixed with concentrated hydrochloric acid to form a paste, and then this is been put on a platinum loop and is introduced into a non-luminous flame. So you are trying to burn it, and then when you observe, right, this cupric chloride as well as strontium chloride, you are doing this with two substances. So cupric chloride, so when you are putting that on the platinum loop, cupric chloride is giving out green color and strontium chloride is giving out crimson red flame. Crimson red flame. So what do we understand from here? So that means every element or every matter has its own way of emitting the light radiations, right, in a particular wavelength. So a particular wavelength will be having a particular color in visible region. All 7 colors have 7 different wavelengths. So every specific wavelength will have a specific color if the wavelength emitted is of visible radiation, is within the range of visible radiation, then you can see the color. So therefore, so each element gives out its own characteristic color. So these color correspond to certain discrete wavelengths of light and are called line spectra. Beautifully given in your textbook. And usually every atom will be giving out, or every element will be giving out certain colors in discrete packets of energy emitted, and each energy will be of a one line, and this is called line spectrum. So atomic spectra is like means all the atoms give out some radiations, and those radiations form in the form of line spectrum. And by the study of these line spectrum, what is the wavelength of the emitted light ray? From that wavelength, you can find out the energy of emission. From that energy of emission, you would come to know that from which energy level is the electron falling into the ground state. That means how much energy is emitted as the electron is jumping from which energy state to the which energy state. That means this gives us the inside picture of the atom, and thus many unknown atoms or the elements can be discovered by the study of the line spectrum. Okay, so this is what like the scientists have proposed for us, and of course Bohr started explaining this and tried to explain the hydrogen spectra based on this line spectrum concept. Let's see how to do it. So according to Bohr, you know that all the electrons are in different orbits like KLM, right? And you know this already previously also. And each particular orbit corresponds to a particular energy level. So E1, E2, E3. Like see, suppose an electron is jumping from like E2 to E3, that means it is absorbing some energy. It is taking some energy from the surroundings or from any other process that is from outside, and then it is getting excited and then jumping into the next orbit. So like suppose here if I say that an electron is in the E1 state, energy state E1. Now it is taking some energy and it got some more excess energy, and now it jumped to the next energy level E2, that is called excited state. So whenever an electron belongs to its own energy state, that is called the ground state of the electron. It is not necessarily even always, right? Ground state of the electron. And whenever the electron jumps into the next state, that next state is called the excited state. First, suppose any electron whichever is there in excited state can never be stable. It can never be stable. It gives out energy and then comes back to its ground state. First, suppose if I say that from E2 an electron has jumped to E3, and now E3 is in excited state. That means electron is in excited state. Now it is ready to give out energy. See, it is giving out energy and it is falling to E2, which is its ground state. So that means here emission is taking place and here absorption is taking place. So whenever it is emission, usually we take it to be like bright lines will be formed. Whenever it is absorption, so dark lines will be formed. And always the energy whichever is either absorbed or emitted will be measured in terms of packets, each packet having an energy of h nu, right? And that means in integral multiples of h nu, always energy either emitted or absorbed is measured in integer multiples of h nu, that is energy packets. Hence we say that each state of or each orbit is having some fixed certain energies, those are which are quantized. So each orbit is having its specific energy, and thus whenever an electron belongs to that particular orbit means that electron is having that energy. Okay, so this is what Bohr is able to explain based on the emission and absorption. Right, and but he couldn't explain. See, he had taken the hydrogen atom into consideration. In hydrogen atom, you have only one electron, and at most we talk about the the first orbit only. It will be in S orbit. It is occupied in S orbit. So suppose if it is absorbing some energy and getting into the next orbit, or from the next orbit it is falling to the ground state orbit or ground state energy. So it is only one transition is taking place, like from one particular orbit to the other orbit, whatever the transition is taking place. That means either one line of absorption or one line of emission should be observed in the line spectrum of hydrogen atom. But to his surprise, or practically when it is observed, when the line spectrum of the hydrogen atom is observed, it is not one line but it is combination of lines. So that is what fine lines are observed in the line spectrum. And Bohr could not explain these fine lines. Why are we getting these fine lines? Why are we getting multiple lines instead of one particular line? This Bohr could not explain. That's a limitation of Bohr's model of hydrogen atom. Then it was corrected by Sommerfeld, right? So he said, like, instead of like keeping the first orbit as spherical, he gave the next orbits as elliptical in thing. So in the he added one elliptical orbit in one orbit and two orbits in the next one, and then three orbits in the next. So he increased the number of orbits in like what do we say, elliptical orbits in place of one spherical orbit. So such, and also he proposed that the nucleus of atom rise at one of the principal foci of this elliptical orbits. So therefore, all the except the first spherical orbit, remaining spherical orbits as proposed by the Bohr are replaced by the elliptical orbits. And then thus he says that instead of one orbit, if there are two orbits, then the transition takes place not between one, but it is bunch of orbits, or it is because of number of orbits in between. So thus he says that we are able to get the fine spectral lines. It's only because that one shell to another shell, in between you have some other orbitals, and because of these orbitals the transition is taking place at multiple levels, and hence we are getting a line spectrum. But he could not explain the line spectrum that is formed for the atoms or the elements which have the atomic number greater than 1. That means other than hydrogen atom. Suppose if you go to helium itself, it could not be explained. Right? That means with an atomic number 1, that is only for hydrogen he could explain it, but for not the other elements whose atomic number is greater than 1. So that is the failure of Bohr-Sommerfeld model. And also Sommerfeld could not explain how come that electron which is there in a spherical orbit is able to continue its movement in the same without being attracted towards the nucleus which is at one of the foci. So that this is the one thing, because the spherical orbit means you can explain it saying that equal forces will be acting on it at every point. But when it comes to elliptical orbit, so at sometimes this electron is far from the nucleus, and sometimes the electron is very close to the nucleus. Then Sommerfeld should explain that, is it not? That why that the electron, when it is coming so closer to the nucleus, suppose if the nucleus is here, so you can see that when electron, when it is here, it is very far from the nucleus, but when electron is here, it is very near to the nucleus. Obviously, it should go and cling to the nucleus, or it should experience more and high pulling and force towards the nucleus. So Sommerfeld could not explain this. Why is an electron able to revolve stably in a specific elliptical orbit? So these are the limitations of Bohr-Sommerfeld model. Very interesting topic, children. This already done many a times in foundation classes as well as in introduction classes of chemistry. And please give a reading and try to underline each and every point in this. This is theoretical. See, whenever a lesson is totally theoretical, you cannot guess what kind of question can be asked from it. So always anything related to the scientist, related to the year of means discovery, everything can be asked. So please give a reading to your textbook and then be thorough with each and every line from the textbook.